Okay. Now, before we begin, I would like to introduce Sir to our audience. Our speaker, Dr. Arijit Bhattacharya, is an associate professor at the IISER Pune Physics Department. The broad subject areas of his research are statistical physics and complex systems. He is interested in understanding complex systems as manifestations of some general principles of statistical physics. Some topics that his present work is based on include directed transport under equilibrium conditions, pattern formation, biophysics, molecular self-assembly, networks, and synchronization. With this, I would like to hand over the virtual mic to Sir to begin the talk.
Thank you. Okay, so I have started sharing my screen. I think you guys have started, seeing my screen here. So let me go to the top. Okay, I'm just going to give a, short talk here, which should be basically introductory to this problem of EPR paradox and Bell's inequality. Can someone just let me know whether you can see the screen properly?
Yes, sir, we can.
Okay, that's fine. Um, you know, Quantum mechanics is a very successful theory that we have been applying, almost 100 years now. Uh, but we do not understand many things of the quantum world the way we understand it, for classical systems. And since the beginning of, the development of this theory, quantum theory, questions were asked by people, uh, none other than Einstein and many others regarding the validity of the structure of the quantum mechanics that we use, whether this is a complete theory or not. But till that, there has not been any real advance in that front, meaning being able to develop a theory which is better than quantum mechanics, gives us an idea about nature in the places where quantum mechanics is opaque. It does not let us know see things, and the argument goes back and forth uh, in this way. So what Einstein had told in the context of quantum mechanics, this is a famous you know a comment by Einstein that God does not play dice. So in Einstein's mind, the thing that was um, concerning the structure of a theory of nature. I mean, that has to be, I mean, what Einstein thought, that a theory has to represent each and every part of the reality, which obviously quantum mechanics does not do. Particularly, this concept of a collapse to a state. A quantum mechanical state, as you know, is basically a superposition of many states. And as you do a measurement, the system collapses to one of the eigenstates of the operator corresponding to that measurement that you are doing. This gives rise to a whole lot of conceptual problems, which we would get to see in this EPR part of the paradox. So Einstein never really liked quantum mechanics. And the theory of quantum mechanics that we basically do these days, that is so successful, that was developed by Bohr and Heisenberg and many others. And to counter Einstein, I mean, Niels Bohr once had told Einstein, stop telling God what to do. I mean, the Bohr's idea was that you have to accept the way um, the nature is. So there, I mean, another way of saying what Bohr had told to Einstein is that, I mean, we are basically classical, our experiences are basically classical. So there exists something in nature which is quantum mechanical, and we cannot really, see through it. We have to develop a theory which is effective in some sense and gives us the classical observations of those quantum systems that we normally do in a consistent way. So that is where probably Bohr tried to imply, in this statement, that there are probably things happening in the nature which, because of being classical beings, have our limitations. We probably cannot see those beyond a limit. Now, these things were going on in the early days of creation of quantum mechanics, and then comes the statement of this guy, who probably sums it up. Feynman says that nobody understands quantum mechanics. Um, that may be true, to some extent, because of the kind of limitation, that I told you, we have, or our instruments have, because the measurements that we do, those basically give us classical results. So beyond that, so far, whatever structure we have in this quantum mechanics is something very effective, but does not really, it appears that it does not really let us see nature in the kind of details we would like to see, from our experience of the classical world. So where the problem is, so then we have to understand first where the problem lies in this, interpretation of quantum mechanics, and that the problem was actually pointed out in this EPR paradox by Einstein, Podolsky, and Rosen. And let us try to understand what they tried to say, in that paper. And what we're going to use here is this Bohm's version of the thought experiment that they had actually used in that paper to show the problem of quantum mechanics. So here, as you see that it is considered a neutral pion, pi 0, that basically dissociates into two particles, one electron, the other is positron. Say the electron is moving, on the left hand side towards left, and the positron is moving towards right. If you consider that the neutral pion was stationary in the beginning, then there is momentum conservation. So, and this pion does not have any spin, but these two electrons, I mean, one electron and the other being the positron, they are fermions. They are half spin particles. So as it dissociates into these two particles, and considering this to be stationary, you can imagine that these two particles are moving with the same, having the same mass, kind of moving with the same velocity. So if at a distance here, if you make your instrument, say a Stern-Gerlach apparatus, interact with this electron and find out what's the spin of this electron, that spin, say you get plus half, then at a similar distance on the right hand side, from the instant, when I'm talking of the distance, it's fine, it takes care of the time because they're moving with the same velocity. Similar distance or beyond that, the spin of the positron, if measured by someone, would be seen to be, if the spin of the electron was plus half, this would be seen to be minus half. Spin of this positron would be seen to be minus half, because the angular momentum has to be conserved. So if it has a up spin, then this particle would have a down spin. Okay. Now that is fine. The state of this electron-positron pair, which is a singlet state, because the total spin has to be 0, can be written in this way, where you can consider this A to be the electron and 1 to be its spin, B to be the positron and 2 to be its spin. So say A, the electron, is 1 meaning say plus half spin, and B, the positron, 2 meaning it has a minus half spin. And there is another state, A having a minus half and B having a plus half spin. So this state of electron and positron is a linear superposition of these two, that electron can be plus half up and the positron can be minus half, or electron can be minus half and the positron is plus half, or electron up, positron down, positron up. Now these two particles are in this state so long you are not observing, you are not making any observation on the system. So it's a superposition of these two states, equal superposition of these two states. It's an entangled state, meaning that you cannot write it just in the form of a product. It's a sum of two products, or it's a sum of more than two products for more complicated states. You just cannot write it in a product form. That basically is the structural signature that this is an entangled state. So the entanglement means that there is a correlation between these two. When one particle has upspin, the other one has downspin. Problem happens the moment you measure it. Say you measured and got this electron to have upspin. From that moment, the positron has a downspin. So from that moment, this positron becomes a classical particle. The moment you have made, before that, there were superpositions. There were probabilistic existence of spins of these two particles. The moment you have made a measurement here and have found out that the spin is up, from that moment onwards, the other particle, however far away that is from this particle, it becomes a classical particle. It collapses into a spin state, which is just the opposite spin, with a definite spin, opposite of the one that this electron had in this measurement. Now, what is up spin and what is down spin? That depends on which direction you are calling to be up and which direction you are calling to be down, right? You can actually orient your Stern-Gerlach apparatus, in any direction, and call a particular direction to be up and the other direction to be down. Say, you can imagine it in this way. When the electron and positrons were created here, at the moment they got created, say the electron was up here, up spin, and positron was down spin to conserve the momentum, and they kept on moving in this direction, in this way. The electron on the left, positron on the right. So they are maintaining a correlation that electron is up in a particular direction and positron is down along that particular line in the other direction. You have measured electron, you have got the positron to be in the other direction along the same line. But that z-axis, you can actually rotate in any possible direction. And even after that, if you get your electron to be positive, up, you get the positron to be down. And if you get the electron to be down, you would get the positron to be up. So this thing, that you can rotate the z-axis, whatever you are calling to be your z-axis, along which you are measuring the spin, in any possible direction, tells you that if there has to be a locality in the Einstein sense, that is, if there has to be a correlation between the spin of this electron and positron at the time of formation, that correlation has to be maintained in all the three components of the projection of the spin, that is sigma x, sigma y, and sigma z, in all three components of the spin if you consider the spin to be a vector, right? But you know that this kind of a half spin particle that lives in a space which is just two-dimensional. You can write down its wave function using just z up and z down, or x up and x down, or y up or y down. You have to just take into account only one direction, and up down orientations give you two eigenvectors, and using that you can write down the spin state. But this experiment tells you, since your z is not determined initially, the direction of z that this Alice probably is going to use to measure electron spin, and you can rotate it in any direction, and despite that rotation always this anti-correlation would be there, then if there has to be any correlation maintained between these two spins, that has to be in all the three components. Otherwise, it cannot happen that whenever in whatever direction you measure an upspin for the electron, you would be having along that line a downspin for the positron. But quantum mechanics is done for a spin half particle in a two-dimensional space where, say, along the z direction, you are considering the spin and its up-down, eigenstates. That gives you the quantum mechanics of the spin, right? So there, the objection that EPR put here is that this theory of quantum mechanics cannot be a complete theory, because this theory only takes into account one direction. You cannot take more than one direction of spin, because this spins spin angle, this angular momentum in different mutually perpendicular directions, this Lx, Ly, Lz, or sigma x, sigma y, sigma z, they do not commute, right? If they do not commute, they are not going to share the same eigenstates. So that is where you have to only take into account the eigenstates of sigma z. Conventionally, we do that, or sigma x or sigma y, and that gives you every information. But here, this analysis tells this, Gedanken experiment analysis tells us that there is some information missing, which has to live in at least a six-dimensional space, along x, along y, along z, and say up and down. We are only using a two-dimensional space. So information of other, say, 4 dimensions are missing in the structure of quantum mechanics. Okay, it works fine. Whenever we do the experiment, we get to see things that because of the anti-correlation, whatever spin I'm going to see here, if it is up, on the other direction it is down. But as a theory, structurally, it's not complete. It's not telling us how all the correlations are basically maintained between these two particles as they dissociate and go away from each other. So that was the main objection. And that is where they said that this theory of quantum mechanics is not complete. So there are other variables which this theory is not taking into account. For example, when it takes into account only the sigma z or Lz, z component of the spin, it's not taking into account the information of sigma x or sigma y. So that was the EPR proposition, that to make this theory complete, you have to take into account those variables. Now, those variables are not there in quantum mechanics, so that is why they are called hidden variables. And from then on, people tried to, include or improve quantum mechanics by including the hidden variables in it. So then came John Stuart Bell, with this, Bell's inequality, which basically showed that quantum mechanics, whatever it is incompatible with the idea of existence of hidden variables. Okay, people were trying to put hidden variables to make the theory of quantum mechanics more complete, following this argument of EPR. But what Bell showed that, I mean, in a very, very simple way, which I'm going to, show you in a minute, that this idea of hidden variables is incompatible with quantum mechanics. What it means is that as a theory, whatever quantum mechanical theory has been created, I mean, you cannot just introduce there in that theory any more hidden variables. Okay, if you do that, the kind of results that you would be getting by introducing those hidden variables, those are not consistent with the results we get from the quantum mechanics. And we know that the results that quantum mechanics gives us, verified by experiments to a great extent, and that works. Okay, so that is where experiment tells us whatever results quantum mechanics gives us, those are reliable, and deviation from that, I mean, there is no experimental support for that. Okay, now, so what did Bell do? So what Bell considered is that the measurements on the left hand side say there is Alice, and on the right hand side there is Bob, and the detectors of Alice and Bob, those just can not only be parallel and anti-parallel, but they can be in any orientation. They can be at an arbitrary angle with respect to each other. So that was the basic consideration of Bell's. So if the detector A is the detector that Alice is using, and detector B is the detector that Bob is using, and say if the detector A is up, that is Alice's detector is up, and detector B is down, so Bob's detector is down. Just consider they are parallel, but one is in the up direction, the other one is in the downward direction. Now, in that case, if Alice measures a +1 spin, Bob would also measure a +1 spin, right? Because due to the anti-correlation, the direction of the detector is telling you which one is the plus direction that you are measuring. Okay, so the direction, this arrowhead basically tells you if the spin is in this direction, then you would call that to be +1. That is in the direction of the detector. Then you would be calling it +1. And if the spin that you measure is in the opposite direction of this arrow, then you would be calling that a negative spin, a -1 spin. Okay. So if Alice measures a +1, that is the spin it measures is in this up direction, then because of the antisymmetry, the spin that Bob would measure, keeping his detector downward in this direction, is a +1 again, right? And when their detectors are parallel, I mean they are in the same direction, then if Alice measures the spin to be +1, Bob would measure the spin to be in the opposite direction to its own detector, that is the B detector, and Bob would measure a minus spin there. Okay, so that is where if you make a projection of Bob's spin on the Alice's spin, what you are going to get here, that is this minus A dot B, right? That's because of the definition of the direction of the spin, that the direction of the detector basically determines what you are measuring, whether the spin is +1 or -1. Okay. So this is something, this is the quantity that you have to keep in mind, that the projection of the spin, Bob's spin measured on Alice's spin, is basically going to be minus A dot B. This minus sign comes because of this antisymmetry, okay, or anti-correlation. These spins are always opposite to each other. Okay. Now, given that Bill made one advancement to this thing, I mean, Bill included a few one more thing to this idea. That is that consider there exists some hidden variables which have not been taken into account quantum mechanics. The theory of quantum mechanics that we know that does not take into account the presence of some variable which, say, let us call lambda, and this is the hidden variable. So if the lambda is actually present there, which we have not taken into account into quantum mechanics, then say this A of A lambda, which can be +1 or -1, is representing the measurement of the spin, which was previously we had considered to be only small a or small b, right? In the previous slide that we had considered to be, these were the spins, A and B. Now, since Bale takes into account an extra variable lambda, there the value of that spin is now written, represented by this A of A and lambda, where this small a or small b can appear there, or small c can appear there. This thing basically stands for your detector's direction. And this lambda is basically the hidden variable which was absent. Now, if you do a measurement of that spin, you are going to get a +1 or -1 depending upon the direction of this A. And of course, depending upon what this lambda, the moment you take into account that a hidden variable plays some role into the, what the spin is in the measurement of that spin. So this A of A lambda and B of B lambda, which are now basically, replacing this A and B, those are measures of those spins. And consider that this is that dot product. This A of A, this big A of small a and lambda, and big A of small b and lambda, with this negative sign outside, is basically this thing, minus A dot B, where this is the spin measured by A detector, and this is the spin measured by the detector B. This minus sign basically comes because of this anti-correlation, and this is that dot product. Only that dot is not written here. Now, since this product also depends on lambda, this hidden variable, and we do not know how the lambda appears in the theory, but we are considering that the lambda actually appears in the theory. So the lambda appears in some form with some value that we really do not know, because we do not know how functionally it appears, but it appears. That is a certainty. So we can actually introduce here a distribution of lambda, which is rho of lambda, the kind of values this lambda can possibly take being inside that theory, and use that distribution to do an average of this dot product to take into account the effect of the dependence on lambda of these spin measurements. Okay. So the only condition that this distribution, the only condition that this distribution has to satisfy is this. There has to be a normalization condition, that there must be some value of lambda there in the theory. Okay, so this normalization condition that rho lambda d lambda is equal to 1 ensures that there exists a hidden variable, and the system takes in into care some value of this lambda, and that is where this is the only condition that the lambda basically follows. I mean, rho lambda basically follows, the distribution basically follows. So this is a measurement when your left detector is A in a particular direction, right detector, Bob's detector is B in another particular direction. The same thing we can write for another pair of these detectors A and C. Here C, say A is the same, the orientation of Alice's detector is the same, but Bob's detector has changed direction a little bit. So that is where this PAC in the changed condition is this thing. Okay. Now, when Alice's detector is A in a particular direction and Bob's detector B is also exactly in the same direction as the Alice's detector, then this product becomes this, right? A lambda, A of A lambda and A of A lambda, because B has become A. And since I have already taken the minus sign, anti-correlation outside, then this thing is going to be 1. So A of A lambda square or A of B lambda square or A of C lambda square, when it's square, its value is 1. Okay? Keeping these things in mind, let us just take into account this difference, PAB minus PAC. Okay? When Alice's detector was along A, Bob's was along B. Alice's one detector was along A, Bob's was along C. And the measurements that they do, projection of that, these PABs by definition, the projection of that, a difference of these things. The right hand side is this by our definition, the way we have written things down. Now what you can do, since you know A of B lambda squared, this is 1, we have seen it already, you can introduce that here between this A of A lambda and A of C lambda, and then just take this A of A lambda, B lambda common, take it outside, take this thing outside. What is left here is unity, and what is left here is one of these A of B lambda and this A of C lambda. So you get this thing here. Okay. Now this is a dot product that, as you know, so its value projection of one spin on the other spins having the same magnitude. So this thing is having a value which is a fraction between -1 and +1. So this quantity is a fraction lesser than 1. And this quantity, this whole quantity, is basically positive definite. That you know for sure, right? Because this being a fraction, this thing, at least this is 0 or greater than 0. Rho by definition being a distribution is more than 1. So this thing is positive. Because this thing is a fraction less than 1, you can write now immediately this relation that mod of these PAB and PAC, mod of this thing is going to be less than this. I mean, if you just drop this part, only integrand is this much, is less than this, less than equal to this. So this is the Bell's inequality. Now, when this part integrates 1, it basically, this part multiplied by 1 integrated gives you this 1. And rho lambda, d lambda, A of B lambda, A of C lambda integrated is basically by definition is your P of BC, right? P of BC, that's by definition, the second integral gives. And that is the Bell's inequality. Now you see the problem here with the quantum mechanics. So if the hidden variable exists there, this has to be obeyed. This inequality has to be obeyed. Now, Consider that Alice's detector is in this direction, A. Bob's detector can stay in two different directions. One is this, perpendicular to the direction of Alice's detector and at an angle 45 degree. So that perpendicular, we call that to be B, Bob's detector. And C, the other one, which is at an angle 45 degree to Alice's detector's direction. Now say Alice detects a plus spin here, plus 1. What would Bob detect? The moment Alice detects her spin to be plus 1, from that moment onwards, Bob's spin has actually become definitely minus 1. That has become a classical spin, right? As I told you, because it has collapsed to a state. So when Bob makes a measurement in a direction perpendicular to that, Bob is going to measure 0, right? So in that case, this PAB is going to give you a 0. Similarly, if Alice detects the spin to be, say, plus 1, and Bob's detector is, in the C direction, then there is a 45-degree angle. And because Bob's spin has become a classical spin following the collapse, this AC, PAC is going to be, this 0.707, that's your cos 45 degree, right? And similarly, this projection, this PBC, which basically have a 45-degree angle between them, that is also going to be this cos 45 degree 707. Okay. Now, if you put these values here, your left-hand side, this AB is 0. So this one becomes 707. You are taking a mod, minus sign goes away. So it becomes 0.707. The right-hand side becomes this, 1 minus 0.707, that is 0.293. You see a clear violation of Bell's inequality, where the right-hand side has to be bigger than the left-hand side. You are having your right-hand side is smaller than the right-hand side. Sorry, right-hand side is smaller than the left-hand side. So people have tried many quantum mechanical situations to see, this is a simple situation, based on that Bohm's, prescription that we have seen here, that Bell's inequality gets violated. So what does the violation of Bell's inequality tell you? So it tells you that what Bell had considered, that there is something missing in quantum mechanics. Those are hidden variables, and those are to be included in the theory to make the theory complete, according to the prescription of Einstein, EPR. But it turns out that the way the quantum mechanical theory has been formulated, it cannot accommodate any hidden variable, because the way the Bell's inequality has been derived, it's so general. It does not take any functional form for the dependence on the hidden variable. It just takes into account the presence of the hidden variable on top of whatever quantum mechanical theory that we have done. And even just considering that presence, which can happen in many different ways, even, given that kind of a very general situation which can be adjusted, quantum mechanics violates that. So it tells you, but the problem, as I told you, quantum mechanics is fully supported by experiments that we have been able to perform, till date. So it's something, I mean, the theory that we use, that is supported to such a great extent by experiments. There is almost no deviation from the theory, appreciable, deviation from the theory. So it's very difficult to think that this quantum mechanical theory is going to be wrong. Okay. So if there has to be a theory which should give you a more detailed description of nature, the way EPR wanted to have it, that is having all the informations, correlations along, all the three mutually perpendicular spin directions, things like that, which quantum mechanics does not give us. I mean, if you really want to, or if you really have to, at some point in time, in future, maybe, develop a theory where there would be more variables present in the theory than the quantum mechanics takes into account at present, that probably is going to be a very different theory from quantum mechanics that we do. Okay, and one has to understand then what's the actual quantum mechanical limit of that theory in an appropriate way. So the violation of this, Bell's inequality, it does not rule out a better theory, say, which is more consistent with our classical perceptions. But it tells you that the existing quantum mechanical theory cannot accommodate those, hidden variables or more variables. In that way, it's complete. Okay, whatever variable it deals with, and that's it. I mean, you cannot add more to that. Okay, once you have a well-defined Hamiltonian for a system, I mean, that basically tells you what are your variables. Okay, that's it. So whatever I have told you here, I have followed, something. Why is it like that? This, there are a couple of sections in the Griffith's book, towards the end of Griffith's book. For more details, you can go through that. Okay, thank you for listening to it. So, have I lost you guys, or you are able to listen to me?
You were audible, sir.
Okay, so I think that's it. I mean, that's what that's all I wanted to tell you about this EPR and Bell's inequality. So if you have any question, you want discussion, you can just go into that now.
Sir, there is one question in the chat.
So what's the question?
Okay, so the question is, so basically we can say that Bell's inequality is like mathematics, and hence if quantum mechanics is right, there is no way for Bell's inequality to not be violated, right?
No, I didn't get it properly. Is the question written somewhere?
Yes, sir. On this one.
Okay. Avinav, is it the question of Avinav's? Bell's inequality is like mathematics, and hence if quantum mechanics is right, there is no way for Bell's inequality to not be violated, right? No, I mean, okay, it's mathematics is correct. I mean, every theory that you formulate in, in physics or in whatever natural science, you using mathematics, that's mathematical. But you have to keep in mind what basically is going behind that mathematics. So in the derivation of Bell's inequality, what goes behind that mathematics is the fact that consideration of the presence of some variables in most general way, okay, such that the variable exists for sure, which is ensured by the variable exists for sure, that is considered in the theory, which is ensured by the normalization of that rho of lambda. Okay, and in the presence of that variable, the quantity that we have been considering previously in quantum mechanics, which was projection of one spin on the other, defined as minus a dot b, minus because of that anti-correlation. Now, in the presence of that variable and a distribution of that, you are taking an average of that quantity or whatever quantity you have been previously considering in quantum mechanics, an average of that on that distribution of the hidden variable. So this is a very, very general, uh, you know,
But
physical.
sir, like, are there any other experimental setups wherein we have observed Bell's inequality being violated?
That's what I told you. So far, till date, there is no such quantum mechanical situation where you would see the Bell's inequality is, I mean, the result is in agreement with Bell's inequality. Everywhere it's violated.
Oh,
Okay,
okay.
so that's the point. So as a theory, it's perfect, and its physical interpretation is also perfect because it's so general. But quantum mechanics, the way it has been formulated, its results experimentally verified that quantum mechanics violates Bell's inequality. Okay,
Yes.
everywhere. So that tells you the basic assumption of Bell's inequality, that there exists other variables, other hidden variables on top of what is considered in quantum mechanics, is inconsistent with the structure of quantum mechanics. That is one. Two is that this structure of quantum mechanics gives us results which are so well, verified by experiments, which go so well with observations. So it's very difficult to doubt the structure also, right? So that is where the problem is.
Yes, sir. So, what I like really wanted to ask is, like, are there any physical assumptions taken into account when we are formulating all that derivation? Like, is it all about just like I could not really follow through the proof very like I will look at it more closely.
Okay, which part of the proof? Bell's part or the EPR part?
No, when you were telling about that normalization, so I couldn't really understand why we want that distribution to be
Yeah,
normalized. So is that coming out of some physical, like our understanding of the how it works physically, or is it very general?
it's the most general thing, right? You are considering, say, Bill is taking into account that there exists a variable, an extra coordinate, lambda, which has not been taken into, the structure of quantum mechanics, but that should be there. Now imagine that lambda can possibly have values between, say, A to B. Okay, there is a range within which lambda can have values. How do you make sure that the lambda would be having value between A to B without knowing exactly how the lambda curve goes between A to B? Because you do not know the lambda curve, how lambda basically varies. What
And
you
that is why we assume a distribution.
sorry.
That is the reason because we don't know the
Exactly,
how lambda
exactly. So,
varies.
that is where you take a distribution, and only this much you can consider that this value must be within this. So you normalize your distribution to one within that span. So that ensures that there exists a variable, and that variable takes a value within that given span. Okay, so that's the normalization. And no other condition is imposed. No other condition is imposed on this, on the presence of this hidden variable.
Okay, so thank you. I'll read about this more and then
Okay.
maybe
Okay.
understand it more.
So, is there other question? There is another one, Gopal. I understand quantum mechanics cannot have more variables than it currently has, but can the number of variables be reduced? How can we check if we are not considering more variables in quantum mechanics than it needs to be described, than it needs to describe the nature? Okay, so Gopal, in quantum mechanics, you have seen that it depends on the Hamiltonian. You know, it depends on the Hamiltonian, which basically defines the space. Hamiltonian keeps all the information of the system in it, and then that basically tells you what's the dimension of the Hilbert space in which this quantum mechanical system basically resides. The quantum mechanical system that you are taking into consideration is represented by a vector, right? That is the quantum state of the system, say at a point of time. And the moment you are considering a vector, that vector residing in some sort of a vector space, which is, in the case of quantum mechanics, is a linear vector space, it must have a dimension, right? And you cannot reduce it just arbitrarily. Sometimes it is possible to have reduction in the dimension depending upon what you are looking at. Like, say, if you consider a hydrogen atom, and if you are only interested in its, say, a hydrogen atom having a proton and an electron, and if you are only interested in the spin of that electron, then you would be looking into a subspace of the Hilbert space in which the atom resides, which is a two-dimensional space where that half spin of the electron basically can be defined as a vector, or the spin state of the vector can be defined, right? So in that sense, depending upon what you are looking at times you can go to lower dimensional spaces. That is when the information of the other part of the complete Hilbert space of the system is not relevant to you. That is where you can make a move to another space, but that space has to be complete. I mean, you cannot reduce it even more. You just cannot go, in a spin space which is one dimensional. There you have to make that space complete. You must work with if it is a spin half, then with two orthonormal eigenvectors of that Sz, right? So that's it. So there is no problem actually. I mean, uh, or there is no controversy regarding that as to how you can actually reduce the dimensionality of a space. It depends on what you are looking at. Since you are looking at a vector, and if that vector resides in an n-dimensional space, your whole theory is based on that vector. There is no way that you can actually reduce that space to be less than n-dimensional. If you do not do something physically, that is, bring something in more into your Hamiltonian to make the system go from that n-dimensional Hilbert space to a lower dimensional Hilbert space. Okay, so it depends on the system. Okay, is that okay, Gopal?
So can you hear me?
Yes.
So my idea was when we are looking from the classical perspective, we found that we need 6 dimensions, but in quantum perspective, we found that 2 dimensions are enough.
Yes.
So can there other theory where we don't incorporate Hilbert space, but we care about a new space which is not Hilbert space, which
So
can be less?
Gopal, what I would like to tell you is that you are being too speculative here, right? So
Yeah.
that it's difficult for me to answer
Hmm.
them. There
Hmm.
may or may not be such a thing.
Yeah,
Right?
yeah, correct.
How would I support or rule out your argument?
Yes, that's what the question. Is there a way to actually answer
No,
that question.
no, looking at the quantum mechanics, I just
Hmm.
cannot answer your question.
Yes, got it, got it. Yeah, thank you. Yeah.
Okay. So what is the third question? Uh, is Bell's inequality still valid in the if the distribution is not well behaved? For example, the distribution is discontinuous at certain points. Okay, this question again, gives its own answer. Uh, if something is not well behaved to the extent that you cannot define the integral that you need for the normalization and for those averages that you are calculating, then obviously Bell's inequality is nowhere, right? For this kind of things, I mean, the mathematics that you have done, that breaks down, that does not apply. So obviously, I mean, there is no answer to this question. At least mathematically, you cannot do anything with so badly behaved things, right? Um, Then Kaustav Gupta, why do we take the projection of Alice's spin on Bob's as the average value of their dot product with respect to the distribution of the hidden variable lambda? Yes, because this is a quantity, right? This is a quantity. Alice's spin projected on Bob's or Bob's spin projected on Alice's. This is a quantity. Now, this quantity, quantum mechanically, whatever you know, quantum mechanics, quantum mechanically measured is one thing. And when you take into account that, okay, whatever quantum mechanics I was considering, that was not complete, there is something else existing there. Okay, then this quantity, you I mean, just making the statement is equivalent to considering that the quantity I'm taking into account depends on that variable lambda. So the moment this quantity depends on that variable lambda, so the way it was having its value +1, -1 or other things, those would now depend on lambda as well, depend on what the lambda is. So in that case, what you have to do is that since you do not know the lambda, you have to do an average over all possible lambdas. Because in the end, these projections are basically the averages. What we are talking of here, these projections are basically expectations. And these expectations are the things that you get from your quantum mechanical theory, right? The thing, I mean, your measurement is always like an expectation value. So that is where, when you have been calculating your quantum mechanical expectation, that is some sort of an average, you also take into account the presence of the other variable, which was not so for there. So that's exactly what has been done in those integrals in Bell's inequality. Is that okay? Kostub?
Yes, sir, thank you.
Okay.
Sir, is there a chance for asking one more question?
Yeah, yeah, go ahead.
Yeah. First of all, very nice presentation, sir. Uh,
Thank you.
so my question is, so we saw that we found out the probability PAB or PAC two ways. One was just by taking the projection, which was previously just in quantum mechanics, and then what you did was you took an average over all the hidden variables as well, lambda.
Yes.
So do we expect, so suppose hidden variable was correct, we would have expected these two values to be different, right?
Yes.
Okay, so my question is, when we finally, I think you did it for simplicity, but when you gave that example, you showed that PAB is equal to 0 if B and A are perpendicular to each other,
Hmm.
and then PAC equal to 0.707 or 1 by root 2 if they are aligned at 45-degree angle.
Hmm.
This was done based on just taking projections, right? By not taking.
Okay, thank you for asking this question. It's a very interesting question. And, I have talked a lot, but I didn't really go into this thing. Um, Let me go into that. Okay. So as I'm saying, these are projections. So same, you have Alice's spin to be say this up, and Bob's spin is say down. Okay, and the way the projection is defined, minus A dot B. Okay, so it tells you, say consider this to be your A, Alice's detector, and this is Bob's detector, B. So when Alice sees a spin to be, this is the spin to be up, and this Alice calls to be +1. Bob, because of the anti-correlation, also sees a spin in the direction of its detector. So by the same convention, Bob also calls this spin to be +1, because if it is in the direction of the detector, then it is +1. So this A and B, these are these numbers. This is +1 and this is +1. So it basically gives you a +1. But since you know there is anti-correlation, so these spins are actually opposite to each other. It's because of the convention that this has come +1. You have taken this minus sign outside. Okay. Now explicitly, by taking this minus sign outside, what you are doing here is that you are considering, this projection to be +1, this projection to be +1 as if when they are parallel. Okay. Now the thing is that this projection, when these orientations are like that, this projection is going to be -1, and when these things are, this is going to be -1, is a quantum mechanical certainty. That this thing is going to be -1 is a quantum mechanical certainty. Okay. And this thing is a quantum mechanical certainty because as you do the calculation quantum mechanically, you get this thing without considering hidden variable. And as you do the measurement, you also get this, right? What the quantum mechanical theory gives you without taking into account hidden variable and measurement gives you, these two things are the same. Now, since the measurement gives you this quantum mechanical certainty, whatever you have got quantum mechanically, it is considered when I was taking these integrals, rho of lambda, d lambda, a of a lambda, and similarly a of b lambda, things like that. Although I am taking into account the presence of these lambdas, hidden variables, they can change things, but not to the extent that this is going to alter the quantum mechanical certainty, which is experimentally verified. Okay, so that is exactly where I took this thing, a of a lambda square to be 1. That is, I kind of here disregarded the presence of the lambda. Okay, when I considered that these detectors are parallel. For the anti-correlation, the negative sign is already taken outside. So now I go by what is here, and I then considered this thing to be 1. I considered means the way Bell has, or the presentation of Bell's inequality, derivation of Bell's inequality in Griffith has considered. So I think this is where your question is. When I'm just putting this thing to be one, I'm practically not taking into account this, the effect of this lambda, because this situation corresponds to a quantum mechanical certainty. Okay, and that has to be there. That's an experimentally verified thing, even in the presence of lambda. Okay, so that is why it is done in this way. And I did not go into these details when I was presenting, because within limited time, always not everything come to your mind when you are
Thank,
talking.
yes, sir. Thank you,
Is
sir.
that,
So,
is that it?
yes, sir. Yes, sir. That was it. So basically, the experiments determine these violations.
Yeah,
It's
yeah. You are bringing into lambda, but you are never going, you are never going beyond what is actually experimentally verified.
correct.
So
So the values that you put are experimental. It's only the inequality that you find out that takes into assumption that there's a distribution that is present.
yes, yes,
The experimental results won't change whether there is hidden variable or not, because
yes,
it's just.
exactly, exactly. That's true.
Thank you, sir.
Okay. So I mean that actually goes into this derivation. So is that it?
Sir, there is one question in the chat above. Sir, can you go above?
Okay. What is the question?
Above Gopal Chandra's question. I think you missed it.
Chatterjee Arijit, or which one? Abhinav?
Yes, sir, that one by Chatterjee Arijit.
Chatterjee Arijit. Okay. So violation of Bell's inequality tells us that quantum correlation can exist between two or more space separated systems. So a global state is required to represent them. Is that what meant by quantum non-locality? Uh, okay, first of all, these languages of locality and non-locality I tried to avoid, because these many people use these things differently. Like in Einstein's way of thinking, that two particles are going in two different directions, and whatever distance they are apart, they are maintaining some sort of a quantum mechanical correlation when the state is entangled. So this is a locality. In Einstein's language, this is a locality, because Einstein won't agree with the fact that the moment you are measuring the spin of one particle at a very large distance, almost at the same, from that same instant, the other particle, in whatever other state it was, it just flipped in the opposite direction of the spin that you had measured. Okay, because that requires an information to flow from one end to the other end in almost no time, with velocity more than velocity of light. So there Einstein considered that the correlation that these two particles are bearing, that is from the very time t equal to 0, they got separated. They are bearing that correlation between them. So if the leftward particle has gone with an upspin, the rightward particle has gone with a downspin. So in that sense, they they are local. So this is the concept of locality, that the correlation basically is maintained. When you are talking of non-locality in this context, what you are taking into account is that they are really far apart. I mean, literally they are non-local. But there is a problem with that concept, is that then you have to take into account the flow of information at a velocity which is infinite. Okay, that is not allowed, right? So if we want to go by causality, keeping causality intact, then what we would, the way EPR went, they told that okay, this is a locality. These two spins are maintaining some sort of a locality. This is a, or in other language you would see they call it, it's um, some sort of a physical reality. Okay, that is that these two spins are correlated, and then they attacked the problem from that direction. So they considered that they are correlated, meaning that there exists this locality from time t equal to 0. But even after that, you require more than 2 dimensions for the correlations of these spins to be maintained. Because when you are making one measurement and you are calling this is my z direction, that is completely arbitrary. You can rotate that z direction in any possible way, and whatever be your z direction, you would either get a plus half spin or a minus half spin. You would measure a plus half or minus half. The moment you do that, on the other end, this is going to be just the opposite. Okay, so this is the way I like to think, and I believe the EPR probably proposed the thing in this way. So because I mean, this way of thinking basically removes the problem of that causality. If you take into account that the correlation exists right from time t equal to 0, so there is then no need for having in mind that information has to travel.
So
Uh,
is in a correlation. So when you measure, there is automatically a collapse, and you don't need the travel of information.
yes, you
Okay.
can avoid at least that if you just keep in mind that the correlation already exists from t equal to 0.
Okay.
But then comes the problem that there has to be hidden variables. There has to be the correlations along at least 3 independent mutually perpendicular directions. The spin being defined a vector, say, classically in a three-dimensional space. Okay, so if one likes, one can bring in this problem of causality into this kind of an experiment. That if you do not want this correlation to be there and hidden variables existing, then you fall in the other trap. That is, it violates causality.
Yes.
Okay. So Einstein could not accept anything violating causality. So he avoided that, considering that the correlation has to exist. Then that brought in this problem that there have to be other variables.
So his point was that correlation does exist, but quantum mechanics is not taking that into account.
Yes, no. Here the problem here, that is where the statements people make. We live in a classical world that I told you a minute ago, that what Einstein was taking into account, a, a spin which is a vector in a three-dimensional space,
Yes.
right? So that's the classical concept, and that tells you then require correlations along the x direction, along y direction, and along z direction as well. Whereas in quantum mechanical theory, you just see that it's a two-dimensional space. I mean, you need just two eigenvectors, orthogonal eigenvectors z up and z down. That gives you a spin state. Okay, and that at the same time tells you of a reality which is so very different from classical reality. Now, classical reality, if we start asking question why the classical reality is like that, that is why a spin resides, being a vector resides in a three-dimensional space classically, being an angular momentum resides in a three-dimensional space classically. If you ask this question, why? Do you expect there has to be any answer? Can anybody give an answer? No, right? But we are so used to accepting that classical reality because we our experience has been classical, you know, since our existence is there. We're just so used to, we don't ask that question. But when it comes to quantum mechanics and it gives a reality, we try to understand that reality in terms of our classical reality. And that is where we ask these questions. So this is the argument given by this Copenhagen school, Niels Bohr, and people who basically follow that. So they told, accept quantum mechanics the way it presents the reality to you. You have to accept that reality, quantum reality, in that way. The way you accept the classical reality without asking why it is like that. Okay? But
Yes.
what EPR says is that you have to understand the quantum reality like classical reality. So I think there are no more questions, right? So shall I say goodbye then? Good night to you.
So, sir, we would like to thank you for this very interesting talk.
You are welcome. I enjoyed, talking to you guys. Okay, bye then. Good night.